Okay, hello Math 280 students. Good to see you all. So this recording is actually a redo of the uh, recording we did in class. The recording in class for this example somehow it was incomplete, and so I'm doing a new recording. Since we did go over this example in class, I'm going to just kind of walk through it here, giving the details, and you already have the example in your notes. But of course, what we want to do here is we want to compute the work that this force field does in moving a particle once around a curve C. And the curve C is defined as the curve of intersection of the plane y plus c equals 2 and the cylinder x squared plus y squared equals 1. Okay, and so of course it's nice to get a picture of what this curve is. So if we go into the solution here, here's a picture of the cylinder and the plane, and the intersection, of course, is this curve right here. Okay, this is the curve C. Okay, and it has this positive orientation. That means, of course, is if you were to walk along this curve, the surface that the curve encloses would be on your left. All right, and that's called positive orientation. So if we apply Stokes' theorem as is, we're assuming positive orientation of the curve. So the way the book does this example is they treat, well, of course, the surface is this surface S here, right? That surface S, well, right here. That surface S is the plane, okay, or a portion of the plane. And the way the book does this problem is it treats, and we did this, we covered this also, and it's another recording, another lecture, so you have it as a reference. But the way the book does this is it treats the surface, this plane, as a function of x and y. In other words, z is equal to 2 minus y. And so z can be thought of as a function g of x and y. So this is how the solution, this is how the book treats the surface in example 1 in section 13.7. And to find the work, they of course use Stokes' theorem, but when it comes to the double integration, they utilize a formula that's derived from the key formula that I always like to use. So as we talked about, I always like to use the formula. Let me see here. It's from section 13.6, surface integrals. The formula is the flux integral formula 9. So we're going to use Stokes' theorem to compute the work for this particle, or the work that the force does on this particle, moving it once around this this closed curve C. And of course, see, the closed curve C is in three-dimensional space, so we have to use Stokes' theorem. Well, Stokes' theorem relates that work to a flux integral, and how you compute the flux integral depends on how you're going to, there's really two ways to do it. One is to treat, like in this case, we can say that z, since z is equal to 2 minus y, z then is a function of x and y, and then we can treat, so z can be treated as a graph. It's a function of x and y, and the formula 9 on page 955 for computing a flux integral collapses into another formula. And we talked about that in the previous recording. But again, I don't like to really use that formula. It's just my personal preference is just to be able to stick to one formula. And the formula that I use, Formula 9, the key formula in section 13.6, that formula requires me to parameterize my surface. Well, the surface S is the plane, and the parameterization of that plane, R as a function of x and y, that vector function as a function of parameters x and y, would be right here. So, of course, z equals 2 minus y. Z has no choice, and then x and y are free. And the restriction on x and y is that x squared plus y squared is always between 0 and 1. If you were to take this curve here, this curve C, you know, if you were to collapse that in the xy plane, which is, of course, you know, down here, this is the origin here, you'd have a circle. So the restriction is that the coordinates x and y have to fall inside a circle of radius 1 centered at the origin, and that's what you have here. So what we do is, first of all, we compute the derivative of our vector parameters with respect to x, and then we compute the derivative of the vector of our two parameters with respect to y, and then we take the cross product. And the cross product, so, and we talked about this, so you have it in your notes, but we take the cross product and we get j plus k. Now remember, when you do the cross product, you can do it in two different orders. You can do r sub, the derivative r sub x cross r sub y, or you can do the derivative r sub y cross r sub x. Well, you need to do the cross product so that you get the correct orientation on the surface S. Okay, and the vector j plus k, which is this vector here. Okay, I'll highlight it in maybe in green. This vector here, that points outward from that surface S. So that is the correct orientation. All right, and so now that we have we can move forward. We have to also, using Stokes' theorem, we have to compute the curl of the vector field F. And so the vector field F is, of course, negative y squared I plus xj plus z squared k. And you compute the curl, and the curl, which you've done before, the curl will equal 1 plus 2y times the k vector, which incidentally equals, right, 0 I plus 0 j plus 1 plus 2y times vector k. Okay, and so now that we have computed, we've computed the necessary elements so that we can now find the work for this problem. So, of course, Stokes' theorem says that the work that the force field does in moving a particle once along that curve C of the intersection is equal to the flux integral. This flux integral here, where your vector field is the curl of the vector field F. The curl of a vector field is a vector field. Now I apply that formula 9 from section 13.6, and it's easy, you know, because I've computed the curl and I've computed the cross product of those derivative vectors, and now I can just do the dot product straight. Okay, and again, that formula 9, section 13.6, it always works, and it's important to be able to use it, because you could have a problem where where the surface can't be written as a function of two variables, and then you know you have to then you'd have to use this formula. So I like, but this formula, since it works all the time, that's the one I like to use. So okay, we just do the dot product of the two vectors, and we're going to end up with the double integral over region D of 1 plus 2y dA. Now region D is going to be, remember the restriction. Remember the restriction on the parameters x and y. The restriction was that x squared plus y squared is greater than or equal to 0 and less than and equal to 1. And so that's this circle then. That's going to be this circle here. That's your region D. And so it makes sense to use polar coordinates. So for dA, I replace dA with r dr d theta. And the y is equal to r sine theta. And the r limits go from 0 to 1. Theta goes from 0 to 2 pi. Okay, and so now that we've done that, it's just a double integral problem. And of course, you integrate with, I'm going to integrate with respect to r first. Well, the integrand is r plus 2r squared sine theta. So that means I'm going to hold the theta constant, and so sine of theta is treated like a constant. And so this is the antiderivative for your inner integral. And then, you know, you have an integral with respect to theta. Now it's a calculus 1 problem. You know, you just compute it. And, you know, I think, let's see here, everything looks good. Everything looks good. Nicely, you got two terms that cancel out, and you're left with pi. So this means then that the work that the force field F does in, or the vector field F, the work that the vector field F does in moving that particle once around that closed path C, which is the curve of intersection between the plane and the cylinder, the work is overall positive. So that means the vector field, the vectors, the flow of the vectors, if you think of it as like well, the flow of the vectors is helping the particle move. Okay, so if it's like wind vectors, it's overall the wind's helping the particle move along its path. Okay, so I hope this was helpful, and thank you very much.